Okay, we're starting with question 2. We already did question 1 in class. 7th I did question 2 as well, but we're going to start with 2. We should be able to find the timestamps that I'm going to put in the description to different problems. This number 2, an object is charged with plus 1.5 times 10 to the minus 2 coulombs, separated from a separate second object with unknown charge. So if we call this big Q, our second charge that's unknown is our little q, we don't know what it is, by a distance, that's our r value, radial distance 0.5 meters. The objects attract each other with a force 1.35 times 10 to the 6 newtons. What is the charge on the second object, little q? So there our force is F, the electrostatic force is that guy. We've got Coulomb's law again over here. If we want to find out what this unknown little q is, we're going to isolate that little q first. So I'm going to multiply both sides by r squared. I got k big Q little q. And then I want little q by itself, so I'll divide both sides by k and by big Q. It's a horrible line. Let's go. K big Q and little q. So we've isolated little q. We're good to go to substitute. That electrostatic force at the top right of the screen, 1.35 times 10 to the 6. 5 times 10 to the 6. R squared, don't forget to square it. I got 0.5 meters squared. We want all this in base units, so that means we should have our force in newtons, and we should have our R value, the distance in meters. K is always Coulomb's constant, 9 times 10 to the 9. Big Q is our positive 1.5 times 10 to the minus 2. We want our charges in coulombs, that's the capital C unit, and so if we have it in a different value like microcoulombs or something that we'll see later, we want to convert that to coulombs. Alright, I'm going to start just with the numerator here. I'm trying not to use my calculator till I really need it. So I could square this distance first. That gives me 0.25, that's 0.5 squared, over the same stuff down there, 9 times 10 to the 9, our k value, the constant, and 1.5 times 10 to the minus 2. And that equals our little q. Going back up to the top, I need 1.35 times 10 to the 6. Now I might get to my calculator, 1.35 times 10, remember second and E button. This is a TI-84 I'm using right now, which most people have. Much better than writing times 10 into the calculator. And we've got, usually you can tell it to output this in, by the way, in scientific notation. We just have no scientific notation, it's just outputting the regular number in standard form. It's upstairs. Downstairs I got 9 times 10 to the 9. Remember the capital E means times 10, so the number that comes after is just the exponent in our calculator, so that's 9 times 10 to the 9 times, I got 1.5 times 10 to the minus 2. And quite a large number that I have here, so I probably would like to maybe have this calculator give me the answers, or the output in scientific notation. 1, 2, 3, 1, 2, 3. 2, 3, 1, 2, 3. I need one more 0 there. That can be kind of tough. To get this quotient, just to be careful, instead of relying on what I'm writing down on the paper, I could just go back up to my first answer right there. See what I'm highlighting on the calculator? And I can take that, I say divide it by what's in my denominator. I'm just go with that guy. And I get 0.0025. This is an amount of charge. We've kept everything in standard units or base units, so this is in capital C coulombs is Q. Okay, we're on to question 3. That bird is loud. The electron and proton of a hydrogen atom are separated on average by a distance of about 5.3 times 10 to the minus 11. There's our R value. And find the magnitudes of the electric force and gravitational force that each particle exerts on each other. So two different solutions we're doing. We're saying, what is the electric force? It's an electron, which is negatively charged, and a proton, which is positively charged. It's going to be attraction. We want to know what is the strength of that electrical force of attraction. And then also, secondly, separately, what is the gravitational force of attraction? One of these values is going to be a lot stronger than the other. So I'm going to list out some of the things we know. We have to look somewhere else in our notes to get the masses of these particles. But when we look for the electrical force, Fe, or the electrostatic force, or Coulomb's force, what we're looking for is to use that Coulomb's law equation right there. And so one of those Q's, let's make the big Q our proton because it's a bigger thing, and our small q the electron. And they both have the same charge. One is just negative and one is positive. And that is the elementary charge, which is 1.60 times 10 to the minus 19 coulombs. And you can see that, I think it's on the second full page of the notes, which is technically page 3. This one, with our picture of the classical model of the atom. And we have the masses of each of those subatomic particles, the amount of elementary charge right there that is on each of our particles, the proton and the electron. For the gravitational force, we need to do Fg. This is the universal gravitation equation we got the end of last semester. And I'm just going to call that big M and little m over there, product of the masses, over r squared. We're going to remember that our Coulomb's constant over on the left, K, is always that 9 times 10 to the 9. We round it a little bit, but that's really close to its exact value. And G over here, whoops, big G is the universal gravitational constant. We used 7 times 10 to the minus 11. That's what we were using when we did universal gravitation. So let's see what the electrostatic force is. Electrostatic force, I've got upstairs 9 times 10 to the 9. My charges are of the proton and electron, same amount of charge, elementary charge, 1.6 times 10 to the minus 19. We've got another one, so same number. I could write this as 1.6 times 10 to the minus 19 squared, or I could write them out as separate charges if it helps me keep track of making sure I have both Q's in there. Whatever you want to do, they have the same amount of charge, so you could square it. The R value is 5.3 times 10 to the minus 11. Don't forget to square that, right? This is a common thing. We forget the squared. Make sure we got that in there. All right, this time I'm just going to look at my prefixes, multiplying those prefix values. So up top I've got 9. Follow along with the calculator. 9 times 1.6 times 1.6. 0.6 times 1.6. which should be the same as 9 times 1.6 squared. So I've got 23.04 up top. Deal with my exponents. I've got 9 plus negative 19 plus negative 19. That's 9 plus negative 38. Or I could put it all in my calculator like this. Make sure I'm using the correct minus symbol there. So minus 29 times 10 to the minus 29. All over, downstairs, 5.3 squared. Let's do that, 5.3 squared, since I'm just doing prefixes first. And then I can go back and check by putting everything in the calculator. And then I've got times 10 to the minus 11 squared, so now we multiply. So I've got times 10 to the minus 22, and we're almost there. One last quotient to get. I'm going to do, again, since I'm just dealing with the prefixes first, 23.04 divided by 28.09. Cool beans, 0.820, let's call it, times 10. Now I've got minus 29 divided by minus 22 in the exponents. So we're doing what? Subtracting, so that's minus 29 minus negative 22. Because we're subtracting, and we've got times 10 to the minus 7. That is the force that should be in newtons. We can put this one in the correct format for scientific notation. So that means I want to make this 8.2. So to go from 0.82 to 8.2, I need to multiply by 10. Multiply the prefix by 10 means I need to divide the suffix or exponent by 10. And so that means I'm going to end up with 8.2 times 10 to the minus 8. And that's in newtons. So we've found 1/2 of our solution, the electrostatic force between the proton and the electron. They have the same charge. It's attractive. So you could say, wait a minute, that's when we would have a minus sign in here. If we have a minus sign in there, that means it is an attractive force. And I mentioned that already at the beginning of the question. So I found the magnitude is in red, 8.2 times 10 to the minus 8. And if I write a negative, that means it's an attractive force. If I leave it positive, then that would mean it's a repulsive force. Okay, those plus and minus signs are very useful for us with electrostatics because things can be attractive or repulsive. With gravity now, on the right side, that's always an attractive force. We have our values ready to go for this. Just need to put in our masses. Big G is 7 times 10 to the minus 11. We need the mass of our proton. So I already have that. I have my guided notes printed out. You can flip to page 3 and see in the box where I put those masses. MP is the mass of the proton. That's going to be our big M is 1.673. I make it the big M because it's the larger mass, times 10 to the minus 27. That's in kilograms. We want that in base units because we're getting a force. We want that in newtons, so we need everything in base units. The mass of the electron is 9.11 times 10 to the minus 31, I think. Yeah, minus 31, again in kilograms, all over r squared. It's the same r, so it's still 5.3 times 10 to the minus 11 meters. Upstairs, I'm going to do my prefixes first. 7 times 1.673 times 9.11. And you can try it, see if you're getting the same thing by using the just scientific notation. I'm going to round this to 0.687. But I like to make sure we know we can do it separately, doing the prefix numbers and the exponent separately. Minus 11 plus, I almost did times, plus minus 27 plus minus 31. I've got my minus 69. And downstairs we know we're going to have the same value that we just had with the previous part of the question because the distances are the same. So that's 28.09. 28.09 times 10 to the minus 22. Now let me just check my numerator real quick. Look at the calculator. 7 times 10. I'm using the times 10 function, capital E, our exponent function, to the minus 11 times 1.673 times 10 to the, so much editing going to have to happen, 1.673 times 10 to the minus 27, and then times 9.11 times 10 to the minus 31. And notice to get the same answer, it's presenting the answer on the calculator in the correct scientific notation format, 1.06. So it's divided the prefix by 100, or 2 orders of magnitude. And so it's times 10 to the minus 67. My answer right now in the numerator is 106. So that's why it's times 10 to the minus 69. There's a quick way for me to check, make sure I'm doing stuff right. I'm ready to get my final answer here for the gravitational force. So I've got 106. I'm going to go back to typing in what my rounded value is. Let's go just the prefixes. 106.687 divided by 28.09. I've got 3.7. Let's round this to 3.8. Makes the most sense. 3.80. Times 10, and I got minus 69 minus negative 22. So I got minus 47. This is also in newtons. We're already in correct scientific notation format. That's nice. Now notice a couple things. One, for the FG value, it's attractive, but there's no negative sign here, right? We never put that for when we did universal gravitation, because gravity is always attractive. It is important to note when we see that over here for electrostatic force that the negative does indicate attraction. It is a proton and an electron after all. Notice which force is stronger. My electrostatic force is on the order, don't look at the prefix number, just look at the exponent. 10 to the minus 8 newtons. Okay, well that's still not much, but look how much smaller the gravitational force is 10 to the minus 47 newtons. It's much, much smaller force of attraction. Either way, we might say that gravity and electrostatic force is attracting the proton and the electron, and yet they aren't collapsing on each other inside the atom, right? The electrons stay out here, the protons stay in the middle, even though both these forces that we just calculated are trying to pull them in towards one another. Why don't they go towards one another? How do they stay out there? You could also think of two protons, right, in the nucleus. Well, they're going to have a force of repulsion that is equal to 8.2 times 10 to the minus 8, because they both have the same amount of charge. They're just both positive, so they're both repulsive. So how come they don't go flying apart away from the nucleus? As you probably know, that has to do with the nuclear forces, which we don't know all that much. We're still learning about them, even in modern science. All right, 4. There are 2 left that we're doing. We're only going up to 5. So number 4, 2 identical conducting spheres are placed with their centers 0.3 meters apart. Okay, so that's my R value. One is given a charge of plus 12 times 10 to the minus 9. The other minus 18 times 10 to the minus 9. And those are already in coulombs, so the base unit. Find the electric force, so that means find Fe, exerted on one sphere by the other. So these guys are going to be, first think, attractive or repulsive. One's positive, one's negative, so they're going to be attractive. So whatever force the one charge exerts in pulling the other one, the other charge exerts the same amount of force pulling back in the opposite direction. That's still Newton's law 3, the action-reaction law, where we said the force of object 1 acting on 2 is equal to the same force 2 acting back on object 1, but in the negative or opposite direction. So both are experiencing the same force of attraction. They're pulling on each other. We're going to find out what that force is. So I've got Fe. Always want to show what I'm starting with. That's my Coulomb's law. I got right there. We're solving or isolating Fe. It's already isolated. So we have these spheres. We've got to get our Coulomb's constant in there. We've got a positive, I'll leave the sign in there, plus, times 10 to the minus 9. I could drop it out and just get the magnitude because I've already said, look, they're going to be attractive. So as long as I remember to say that in my answer or put that minus sign back in at the end, that's fine. Minus 18 times 10 to the minus 9 over 0.30 meters. Let's make that actually look like a decimal point. And don't forget that distance is squared. All right, let's for this one just put everything in at once. 9 times 10 to the 9 multiplied by positive 12 times 10 to the minus 9 multiplied by, let's do negative 18. So we get our negative sign in our answer to indicate a force of electrostatic attraction, the minus 9. And I've got minus 1.944 times 10 to the minus 6. Now this thing just output my answer in the calculator there in scientific notation. I don't know how it just changed itself. I don't know why it didn't do that before. But if you go into mode and you go into scientific, that's what will force it to output the answer in scientific notation. I'm not really sure why I just chose to do that. Oh, probably because I put it in as scientific notation. That's why. That's why. All right. I'm so smart. 0.3 squared is 0.09. Okay. And we've got one last step here. I already have my numerator in the calculator still, so I might just go divide that answer by 0.09. I have minus 2.16, so that minus means attractive force once again. Minus 2.16 times 10 to the minus 5. This is electrostatic force, so it's in newtons. No problem. There we go. Minus sign means attractive. We've got a magnitude. That's our number. And so we get a pretty small value, right? Times 10 to the minus 5. But that's our electrostatic force from both our conductors. So one of them's, we'll say big Q, little q, attractive force. This is the force of little q acting on big Q. And then little q feels that same amount of force, the force of big Q attracting it. And we could say our big Q was, let's say, the positive 12. And our little q was our minus 18. So the little q actually has the larger amount of charge. It's just negative. It doesn't matter which one you call big Q and little q, right? You could use Q1 and Q2. The spheres are connected by a conducting wire. Aha, so we take a wire, and they're connected. Conducting wire, so electrons can flow, right? It's like grounding it, except they're not grounding it. We're touching just the two conductors together. After equilibrium has occurred, so remember we did that demonstration with the visual, the little animation on the smartboard in class. Touch the conductors back together after they have different charges. You touch them together, everything balances out. They like split everything up equally, so they're at equilibrium. We gave the analogy of pouring hot water and cold water together. Right? Everything reaches equilibrium eventually. With the electrons, it's pretty much instantaneous, right? They're trying to get away from each other. They spread everywhere, uniformly around and throughout the conductor. Find the electric force between the two spheres after this has happened. Well, once they're connected, this is how we figure out how much charge each one's going to have after they're allowed to touch each other with a conductive wire. Look at the net charge before, so up top, the net charge, I just add these together, plus 12 and minus 18, my net charge is minus 6 times 10 to the minus 9 coulombs. It's really important to be able to identify the net or total charge right there. Right, there's the same in the interactive charging. I recommended to people that you look at the total amount of charge that you have in that interactive, because you needed to then adjust how much each conductor had. But you add them both together to get the total amount of charge. Okay, so after they're touched by a conductor, so let's say after, all that charge, that net charge has to stay the same because charge is conserved, but it's going to spread out equally. So after, one of our Qs, one of our conductors, is going to have a charge of minus 3 times 10 to the minus 9 coulombs, and the other charged conductor will have minus 3 times 10 to the minus 9 coulombs. Take a moment to reflect on why that should happen. The total net charge up here at the top is minus 6. Let's call it minus 6. They have different amounts of charge. You touch them together, the charge is split up equally between two objects. So now one of these is going to have minus 3, the other one minus 3, so they're equal, they've reached equilibrium, but that still adds up to minus 6. Net charge is the same. We've conserved charge. We haven't grounded anything and let charge go anywhere or add charge to it. We just let them balance out equally, so the net charge gets split between two objects. Minus 6 divided by 2, minus 3. Okay, the rest of this then is just saying what's the new force between the spheres. It's our same process of using Coulomb's law. K, big Q, little q over r squared. I would say go ahead, pause now, and just put it in the way you want in your calculator. Times 10 to the minus, or 10 to the 9. And then you can check with my work after. Here, look, they have the same amount of charge, so I could square this, right? Because it's minus 3 times 10 to the 9 multiplied by another minus 3 times 10 to the 9. They both have the same amount of charge over r squared. R is the same. What was r? 0.3. 0.3 squared. So let's do our numerator. Let's just do prefix suffix this time. Then we can put it all in at once to check. So I have minus 3 squared, which is 9. Right? So that becomes positive. They're both negative charges, so they can repel each other. So that's 9 times minus 3 squared, so it's going to be 81. Yeah, 84 is. I have to do it like that because it thinks it's doing 3 squared and then multiplying by negative 1. Look at some, yeah, careful. see what's on the calculator. It's doing, in my first line there where I got negative 81, it's doing 3 squared to get 9, and then it's multiplying by negative 1. So we want to make sure we do negative 3 parentheses squared, just to ensure you get the right signage. But we should know minus 3 times minus 3 is going to be squared. Minus 3 times minus 3 is going to be positive 9. Okay, I have my suffixes or exponents. I got positive 9 and negative 9 squared. So it's going to be minus 18. So I got 81 times 10 to the minus 9. That's upstairs. Downstairs, we still got 0.09 because we're squaring our 0.3, just like we had up here. Right? So prefixes wise, we could say this is 81 divided by 0.09, which is the same as 9/100ths. We wanted to do it without just relying on the calculator. So that's 81 times 100, 8100 over 9 times 10 to the minus 9. 9 times 9 is 81, but I have 8100. So this is 900 times 10 to the minus 9. It's not a 9. Newtons. Let's put that into our correct format, which means I need to divide my prefix by 100. Dividing by 100 means I'm multiplying my exponent by 100. So this is going to become 10 to the minus 7. So we've got 9.00 times 10 to the minus 7 newtons. Notice we have positive answer. So this is now a repulsive force. And let's see if our force is smaller, because we have smaller charges. They're both charged with 3 times 10 to the minus 9. Before it was 12 and 18. So initially we got 2 times 10 to the minus 5. Just look at the prefix. And now we've got a smaller amount of force, which is times 10 to the minus 7. Okay. There's one left, huh? Okay, number 5 is the last one because the rest have to do with electric field, which we'll talk about when I get back. Number 5, 2 electrostatic point charges. So that just means like you don't care about its size. Pretend it's a point. Charges of plus 60 microcoulombs. So this mu, that's mu c. So mu c means microcoulombs. There we go. And micro means 1 times 10 to the minus 6, or just 10 to the minus 6. Just like kilo, right, K in front of kilometer means 10 to the 3. So I say 1 kilometer is 1 meter times 10 to the 3, or 1,000 meters, equals 1 kilometer. So mu is just the symbol standing for micro, like micrometers. Here we have microcoulombs. You just have add 10 times 10 to the minus 6 to whatever the charge value is. It's just a shorter way, instead of having to write out times 10 to the blah blah blah, just say it's that many microcoulombs. Anyway, we've got plus 60 and a plus 50, repulsive. Exert a repulsive force, okay, on each other of 175 newtons. Okay, that's pretty strong. What is the distance between the two charges? So R is what? We're still using Coulomb's equation for electrostatic force. What is the distance? We want to get R by itself, so I'll multiply both sides by R squared and divide by Fe, so that I have K big Q little q over Fe. Then I need to take the square root. Someone's growling. Square root K big Q little q over Fe. Now we're ready to put our values in. I've got 9 times 10 to the 9. One of my charges is 60 microcoulombs. Excuse me. So 60, that is not a 60, Stacy. Put it over here in the margin. just so we see it, 60 mu c, or microcoulombs, means 60, just keep whatever number's there, and then micro times 10 to the minus 6 coulombs. So you see, I just replaced that mu with times 10 to the minus 6. That's all you got to do. And the other one is 50. So 50 microcoulombs is going to be 50 times 10 to the minus 6 coulombs. And again, I'm just substituting 10 to the minus 6 in for mu, because it's just a prefix. All right, let's go. One of them, doesn't matter which one's big Q, which one's little q. So I'm going to go with 50 times 10 to the minus 6, 60 times 10 to the minus 6, over whatever the force is, 175, yes. Now, let's take a moment here, pause. I'm not writing the units because we already have so much stuff written in there. But 9 times 10 to the 9 is always Coulomb's constant. That's fine. And these charges, I've converted them into coulombs now, right? Because the micro is taken care of, and this force is in newtons. We want that because if we want base units so that we get an R value, radial distance between the charges, that's going to be in meters. Otherwise, we'll get a number, and then you won't know what the units are going to be, which we all know how that goes. So we make sure we get it converted into base units. Let's do just everything at once in our numerator, since we've done it so many different ways. 9e9 times 50. I didn't change it to 5, right? It's 50e minus 6, or I could do 5e divided by 10 multiplied by 10. 5e minus 5 times 60. Make sure you're using the exponent function. Don't write times 10 to whatever power. It's a good way to get it messed up. 27. That's a nice answer. 27 over 175. Oh, never mind. That's not a nice answer. I could put this in right away. 27 over 175. I get 0.39. Let's check it with 27 over 175. Okay, so if you're using the graphing calculator or scientific calculator, just keep these values, right? There's no need to round in the middle of it all. So I get that same value. You see both 0.39279. If you did round to, let's round it to 0.1, I'd keep 3 digits there, because I'm probably going to have 2 in the final answer. Because you don't want too much heavy rounding going on in the middle of it all. I still get 0.392. That's in meters. So they're 40 centimeters apart, like a foot, 1 1/3 feet away. And it's 175 newtons of force. That's pretty something. So even though they're microcoulombs, that's a lot of charge. We'll never see in our lifetime 1 whole coulomb of charge. You would probably die immediately. That's the end of 5. The rest of them involve the field, and we will come back to the field later. So there we go.